Let me start by thanking the organizers for putting up this wonderful conference and for giving me a chance to showcase some of the work that we have done over the last several years on frustrated systems. So the topic of my talk is very general, and as you can make out, I'm going to show you snippets of various works that we have done over the past several years. So without any further delay, let me start. So my talk is broadly divided into two parts. In the first part, I'm going to talk about some frustrated materials which we have dabbled into over the past several years. In the second part, I will try to connect with you and tell you a story about frustration in an antiferromagnetic spin half chain. So taking advantage of the fact that we are towards the end of a conference on frustrated systems, I don't need to tell you what the structure of pyrochlore is. So I'll directly come to my presentation. So here is pyrochlore titanates. So R stands for the rare earth atom or ion, which is basically responsible for all the fascinating magnetic properties or ground states that you see in these materials. Titanium is magnetically silent, but very important component of this chemical formula. So on your screen, what you see is a very large, very large, by very large, I mean several centimeter long single crystal of one of the titanates. So about a decade back, we grew almost all the titanates, starting from samarium all the way up to lutetium. And this is, don't worry about the chemical formula because all of them roughly look alike, except for different colors. And what I want to tell you is that titanates are rather easy to grow. You can grow them using a technique known as optical float zone method. So since there was probably no talk on this particular aspect of material, how the frustrated systems are grown, and probably many of the students and maybe also some theorists would not probably know, or maybe may want to know how such nice crystals are grown. I have a little movie to show it to you. I hope it will work. So this is how the crystal growth is done in a float zone furnace. So basically what you do is you take the light from the halogen lamps and you focus it tightly over a very small volume. This volume is typically 5 to 6 millimeter in diameter and about 7 to 8 millimeters in length. So you have 4 lamps. Each of these lamps is about 1 kilowatt. So 4 kilowatt of power, tightly focused over a very small region of space. And that is where you bring your material, which is to be grown as a single crystal. So you cast it in the form of a rod. And you bring the seed crystal and you get this melt over here. And then what you have to do is you have to start pulling this crystal down. And at the same time, in order to feed the zone, this is the molten zone, you have to move your material down at the same rate. And if you do it carefully, you get very nice crystals, as one which is shown over here. So now, the reason why I showed you titanates, I already told you that about a decade back, we did most of these pyrochlores, and our interest was in looking at their phononic properties. So most of these pyrochlores, they show strong N-harmonicity, phonon N-harmonicity. And here I've taken the example of one of the most extensively studied titanate members, which is dysprosium 2 titanium 2 oxygen 7, which is a spin ice ground state. But for this, understanding the data which I'm showing here, you don't really need to know what a spin ice is. In case you don't know, I'm talking to the students right now. So what do you see on your screen? You see the Raman spectra of this crystal, dysprosium 2 titanium 2 oxygen 7. And I'm showing you a very small spectral range, which extends from 250 wave number to about 400 wave number. All right. So in the Raman spectra, from the group theoretic analysis, you expect 6 Raman active modes. So this is one of the modes, the most prominent modes at room temperature. So here's a small mode which is sitting here. So what you do is you start lowering the temperature. So as you lower the temperature, nothing really happens down to the temperature of about 150 Kelvin. But as you cool below 110 Kelvin, a new mode appears around this 280 wave number. And when the sample is cooled down further, this mode becomes more and more pronounced. All right. So appearance of a new mode indicates that something is happening to the lattice, pyrochlore lattice. At this juncture, I should tell you that all the modes, Raman active modes in the pyrochlore structure are due to the vibration of the oxygen atoms. So the rare earth ion or the titanium ion is not involved in giving rise to any of these modes. And the other point to notice is that in lutetium, so this is the section of the spectra at 12 Kelvin. In lutetium, you don't see this new mode, which is designated here as M5. So this is unique to the spin ice pyrochlore, dysprosium 2, titanium 2, oxygen 7. And you can also notice this graph shows the variation of various Raman active modes, their line shift actually as a function of temperature. And you can see anomalous softening for most of these phonons. And you also see changes that are taking place precisely at the temperature where the new mode appears. Okay, so far, so good. Nothing special has happened. We want to understand what is the origin of this mode? Is it related to any structural change? And if it is related to a structural change, it should have ramifications for the spin ice ground state. So there were also suggestions that this new mode could be a crystal field mode, because the crystal field splitting of dysprosium in this particular compound, the first excited crystal field level is around the same energy, which means around 250 wave numbers. So in order to see if it is indeed a crystal field excitation or if it is related to a structural change, we did a very nice experiment where we enriched our crystal specimen with O18. So with O18, we have a heavier ion which is vibrating, all right, but nothing has changed as far as the electronic charge cloud is concerned. Now the crystal field splitting depends on the electric field of the oxygen ions. So since you have not perturbed the charge cloud, if it is really a crystal field excitation, it should not change with this isotopic substitution. On the other hand, if it is a phonon mode, then of course it will get displaced, all right? So this is exactly what we see. We see that both M5 as well as the principal mode, which was already there, both of them have shifted. So this one is data for O16, and here's the data for O18. And both of them have shifted, and not only shifted, even the FWHM has decreased. And since the full width at half maxima is, it scales inversely with the mass of the vibrating atom, it clearly indicates that this mode has to do with the phonons and not the crystal field. And to, really nail it down, we measured the temperature dependence of the lattice parameter, and you see that there's a clear discontinuity around the same temperature where the new mode appears in the Raman spectra. So this clearly shows that this compound Dy2 Ti207 has a subtle structural change which happens around 100 Kelvin. It may not actually have any effect on the spin ice ground state, because the spin ice is determined by the position of dysprosium ions and the spins, but it may change the crystal field excitations slightly because of the displacement of oxygen ions from their regular position. So let's move on. So titanates is a story which is now fading, and what is picking up, what is blooming, is this series Pyrochlore Zirconates. So what is so special about zirconates? So first thing to note here is that the zirconate series, the field of stability, the structural stability of zirconates extends from lanthanum to gadolinium. Now, if you remember, titanates, the first pyrochlore member is samarium. So in the titanate series, you cannot access neodymium and praseodymium. And why these two are important, Nd and Pr are important, because both Nd and Pr have small movements. And Nd in particular is a Kramer's ion. So you get the Kramer's doublet, all right? And so you get an effective spin half on the pyrochlore lattice. And this effective spin half, in fact, get further fragmentized, giving rise to very fantastic physics, which is related to the superimposed ground states with both spin ice as well as spin liquid kind of correlations present together. So our interest here is to grow crystals of this material, but there are issues that are present with respect to crystal growth of zirconates. A, the crystal, the melting temperature is very high. You cannot reach that temperature by the ordinary float zone method that I showed you in the previous slide. B, they undergo a order-disorder phase transition at high temperatures. So when you crystallize them, they crystallize in a defect fluoride structure, and only when you cool them further down, they transform into the pyrochlore structure. And there's a subtle difference between the defect fluoride and pyrochlore structure, which is very important actually, because in these compounds, the leading exchange is to begin with very weak. On top of it is highly frustrated. So these materials are very sensitive to structural modifications, structural changes, which could be because of off stoichiometry or because of real structural changes. So here what happens is that when you grow these materials, and in fact, the crystal growth of these materials was reported as early as in 2016 by the Warwick group. And they grew these crystals again by float zone, but using more powerful lamps, using xenon lamps. The issue is that since the melting temperature is around 2500 degrees centigrade, at such high temperatures, some of the neodymium, it evaporates, it goes away from the float zone. So this results in off stoichiometry, and this off stoichiometry is particularly bad because the neodymium is then replaced by zirconium. So in the common parlance, this is known as anti-stuffing. And the stuffing is the opposite of it, which refers to neodymium going and sitting at the zirconium sites. And both of these are really bad, terribly bad. People have experienced this in ytterbium titanate, Dy2 Ti207. And even as of today, we don't really understand what the exact ground state of ytterbium titanate is, because a very small inadvertent stuffing or anti-stuffing can change the ground state. So our aim was to grow these crystals. And by the way, before I go to our own work, let me tell you that this figure is actually from this PhysRev materials paper, which is from the group of Steve Wilson. And they have a very powerful furnace. This is a laser heated float zone where they can apply very high pressures. So under high pressures, when you carry out this growth, you can suppress the evaporation of the volatile component. So you can see here is the close to the ideal lattice parameter, the lattice parameter that you would expect when there is no stuffing or anti-stuffing, which means that your stoichiometry is really the one that you want. And if you grow crystals by ordinary under ambient pressure, you get a lattice parameter which is much smaller, which indicates that some of your neodymium is gone, which is the bigger ion, and it has been replaced, it has been anti-stuffed by zirconium. So they have grown these crystals at various pressures, and under 70 bar pressure, they come very close to the ideal lattice parameter. So we thought we will grow these crystals by flux method, because the flux method, the advantage of flux method is that you can work at much lower temperatures compared to the melting temperature of the material. And we would crystallize directly the pyrochlore phase, not the defect fluoride phase, which you invariably get when you use a float zone technique, when you're growing directly from the stoichiometric melt. So we could get some crystals, but the lattice parameters are still not up to the mark. So this is a work in progress. And we believe that in some time, we will have these crystals, and then we will be able to explore this interesting new physics, which is related to the moment fragmentation. So again, back to the old stories. I'll not spend much time here because it's pretty old, and the interest in molybdates is fading. So in molybdates, in fact, the field of stability, structural stability is pretty large. But the problem here is that the moly sublattice orders ferromagnetically. And once the moly sublattice is ordered ferromagnetically, then it's very difficult to see what the rare earths are doing. In fact, so and the problem with the crystal growth is that molybdenum, first of all, keeping its oxidation state to 4+ is rather non-trivial, because it tends to go to 5+ or 3+ rather easily, depending on what the growth conditions are. And second, molybdenum oxide is highly volatile. So around 1200 degrees centigrade, it starts evaporating. So we had grown these crystals, and by doing some bulk measurements, we showed that in samarium molybdate, the samarium ions undergo a spin ice kind of freezing at low temperatures in the background of the ferromagnetically ordered molybdenum spins. And this we inferred from the specific heat, but here I'm showing you the bulk magnetization data. And you can see these are the calculated, these are not calculated. This is the experimental data on a classical spin ice compound, holmium titanate. So it shows a easy axis along the 100 direction, which is seen over here, and a step-like transition, which corresponds to a transition from 2 in 2 out to 3 in 1 out state. And then along the 110, you get the hard axis. So this was a bit technical, so let's move out. Now, yesterday, Arnab, emphasized about the stacking fault, and before him, in fact, Natalia also mentioned about the stacking fault, and so was in the talk of Rosa Valenti. So because of the stacking faults, it's very difficult to say what exactly is happening in RuCl3. So I don't want to get deeper into this story. I just want to tell you that we are also into growing RuCl3 crystals, and we have managed to get a large crystal of about 600 milligram with a fairly sharp specific heat anomaly, and which has a very little trace of the stacking faults, if any, because if there are stacking faults, you get these multiple phase transitions, which are indicated here by the with the black curve. So the idea was not really to grow RuCl3, but actually to go a step further, to actually dope it and to investigate the effect of non-magnetic doping. And for the underlying motivation, you can look at these presentations. The bad news is that it's very difficult to dope RuCl3. We tried doping it with aluminum, we tried doping it with indium. And the reason why we took aluminum and indium is because both AlCl3 and InCN3, indium chloride, they also crystallize with the same structure. So they are isostructural to RuCl3, and yet it's very difficult to dope them at the ruthenium site. On the other hand, it's relatively easier to dope iridium, which we have managed to do, and now we are trying some other substitutions. So moving on, we now move to CeCl3. The structure looks deceptively similar to that of RuCl3, and this is in fact a material which has an effective spin half ground state. But the issue here is that it's not a van der Waals material. So you have the cerium connectivity which percolates also along the C direction. So it's not really something which can substitute RuCl3. The crystals are difficult to grow and also very sensitive to moisture. We did some preliminary measurements. We see this very interesting hump over here in the magnetic susceptibility. As of now, we don't know why this is there. This is, by the way, not a Curie-tail. This is the full cerium movement, because at much lower temperatures, it is supposed to order antiferromagnetically. So the cerium-cerium exchange, the theta Curie-Weiss is about 0.2 Kelvin. So I mean, this hump is a little bit of a mystery as of now. Could be related to the crystal field excitations of cerium. The good news is that currently there's a lot of interest on these kind of materials, not coming from the frustrated, directly from the frustrated community. So here, for instance, there's a paper, there's a theoretical prediction about cerium system itself, which says that these chiral phonons can couple with the cerium movement and give rise to very high magnetic fields. Moving on, this is NiPs3. This is van der Waals, and the structure is also very similar to that of RuCl3. So you see this, these violet balls, which is the nickel atom or the ion, forming this honeycomb structure. But the honeycomb structure is there indeed, but it's not perfect. That's one thing. And it undergoes magnetic ordering below temperature of about 150 Kelvin. It is very easy to exfoliate, all right? And the interesting thing, I mean, it's not our discovery, it is discovered by, it is reported in this paper, that down to double layer, 2 layers, it shows the magnetic ordering persists. In the monolayer limit, the magnetic ordering completely disappears. So our interest is to, once again, as with the RuCl3, to investigate the effect of non-magnetic disorder. Here I'm showing you some Raman spectra from this paper. Just to mention in passing that there's some very interesting things happening. So this is the Raman spectra at room temperature under 2 different orientations and polarizations. And this is the Raman spectra in the magnetically ordered phase. And you see this huge background which is appearing here. This is actually due to 2 magnon scattering. And these phonons, so for instance, P9 here, it couples very strongly with this magnetic 2 magnon continuum. And this leads to this characteristic asymmetry of the phonon line shape. And this can only be modeled by the Fano line shape because that describes the coupling of phonons with a continuum. So we have been studying all these in these zinc-doped materials. So we have some interesting results, but I'll reserve them for our next meeting. Let me now move on to triangular lattice antiferromagnet. I hope I'm not going too fast and not sort of bombarding you with one system after another. So this is triangular lattice antiferromagnet. In fact, there was a beautiful talk by Steve Wilson. So I don't really have to go into deep into the introduction. So triangular lattice antiferromagnet is expected to show this 120-degree ordering, which is what you would see even with the classical spins. But what distinguishes a spin half or a spin 1 triangular lattice antiferromagnet is the behavior in the presence of a magnetic field, where you're expected to see a cascade of phase transitions. And the most sort of sought after transitions is this up, down state. This would also appear for a classical spin, but only for one magnetic field, because it will be some state in passing, right? But here you have this persisting over a field range, which extends from HC1 to HC2. So this is the real data. I mean, by real, I mean, this is the data on a compound, barium 3, cobalt, antimony 2, oxygen 9. And these are the theoretical fits to it. So what have we done with this in this kind of systems is that we got interested into nickel system. With nickel has a spin 1, which is still, very much quantum. And a nickel spin 1 is sitting on a triangular lattice. And these triangular layers are sort of well separated by these dimers that are formed by M prime. M prime here is niobium. So these green balls are actually niobium atoms. So these are these edge sharing, sorry, I think it's corner sharing octahedras. So here's the behavior of barium, strontium, and calcium. And barium compound undergoes a single magnetic ordering, which so the ground state is expected to be this 120-degree ground state, which I showed you in the previous slide. In the case of strontium and calcium, there are 2 magnetic transitions. So this is called 2-step ordering. And in calcium, the transitions are not very well resolved. So we decided to grow crystals of one of these, which is calcium 3 nickel niobium 2 oxygen 9, because there were reports that it melts congruently, which always makes us happy, because congruently melting systems, though I have not explained it in this talk, are easy to grow by float zone method. So this is what we grew. And this turned out to be, so this is the crystal that you get from the float zone method. And this crystal doesn't look uniform. It doesn't certainly look good because there are 2 colors. And in fact, these 2 colors are so we could, mechanically extract light green pieces, light green and translucent pieces, and then the dark pieces. So we were curious, why there's a color change. Often the color change is because of the oxygen of stoichiometry. But in this case, it so turned out that this color change is not because of the oxygen of stoichiometry. It is because of the change in crystal structure, which is depicted here. So in the lower panel, we have the calculated XRD pattern for two different symmetries. This is the monoclinic symmetry, which is an ordered structure, B-site ordered, where niobium and nickel are ordered, and the ordering is 1:2 ordering. And then the other one is the structure, which is where the B site is occupied by niobium and nickel randomly. And you can see that, sorry, this is the calculated XRD pattern. And you see that the black specimen agrees very nicely with the red curve over here, which is for the PBNM, the orthorhombic symmetry, because of this missing peak over here. On the other hand, the green specimen is an ordered structure where you have this peak. So the differences is because of the crystal structure difference and not because of oxygen of stoichiometry or any measurable oxygen of stoichiometry. And this is further confirmed by synchrotron data where we solve the structure. So this one is, as I said, orthorhombic with B site occupied randomly by nickel and niobium, and this one is an ordered structure where you have a nickel octahedra followed by 2 niobium and then nickel and 2 niobium and so on and so forth. And this is further confirmed by high resolution TEM measurements where you actually see this ordering along this line. So here you see 1:2, 1:2 and so on. And this is what you see in the intensity profile in the HR-TEM measurements. Good. So we have now both type of crystals. And by the way, finally, we managed to get a nice crystal where there are no two colors. So it's completely monoclinic and it has this ordered structure. So once you have them, you would like to study them. And this is what you see. Again, this is the preliminary study. So from the black crystal where you have nickel and niobium randomly occupying the B side, you would expect a glassy ground state, which is what you see over here. So here the specific heat has a broad hum, which is centered around 10 Kelvin, as opposed to the specific heat of the ordered sample, which shows two sharp transitions, which is what was expected from on the basis of the powder study. So the two-step transitions as occurring around 5 Kelvin as opposed to a broad transition in the disordered sample, which is occurring, I shouldn't say it's a disordered sample, because it's, I mean, crystallographically, it's more symmetric because it's the orthorhombic structure. It's just that the nickel and niobium are now sharing the same B site. And you have the other telltale signatures of, the spin glass or the glassy state. I don't want to go into the details because this is something which is very well known and studied. We also did neutron because of, in the interest of time, I'm not showing the neutron data here. So how much time do I have for the second? Oh, so I don't think I'll be able to do justice to the second part where I thought I'll try to have more engagement with you. So very quickly, in a spin chain, if J prime, which is the interchain coupling, if J prime is 0, then there's no long range magnetic ordering. And this was very, beautifully described in the tutorial sessions by Bella Lake. On the other hand, if you turn on the switching, the interchain coupling, then there's a magnetic ordering. The Tn is calculated using the mean field theory to be given by this expression. This is the size of the ordered movement and so on and so forth. This is very well known. All right. Now, what happens if you have a third interaction, which would be the case in the case of a zigzag chain? So now, besides J and J prime, you also have an interaction between these two copper spins, which is labeled here as JF. And because this angle is approximately 90 degrees, so JF is ferromagnetic. So on this triangular placket, if you take this as a triangular placket, these two are coupled antiferromagnetically, and these two are coupled ferromagnetically. And this is, the recipe for getting a frustrated system, because you can figure out why that should be the case again for the students, in case you have not followed, because you're used to, all three antiferromagnetic, and then you say frustration. But if you have two ferromagnetic and one antiferromagnetic, you can also have frustration. So you can realize this in these two systems. So this is a linear chain So here, blue balls are the copper atoms, which are carrying a spin half, and they interact with each other via this intervening red ball, which is the oxygen atom. So this is the copper-oxygen copper super exchange path. Along this direction, there's no intervening anion, so therefore there's no torque between these two spins along this direction. And along this direction, there could be a path. There is a path actually, but it's rather too long. So therefore, the interactions are predominantly along the chain direction. And sorry. And here the chains are zigzag. Otherwise, the structures are analogous. So sorry, I didn't tell you that this one is strontium 2 copper oxygen 3, and this one is strontium copper oxygen 2. Now, if you want to look at the effect of frustration, by the way, I should also mention that these are the values of J, J prime, and JF for these systems. Here, of course, there's no JF. So you can see that in 112, which has the zigzag structure, the magnetic ordering has been suppressed down to a temperature of 1.3 Kelvin. And in the case of 213, the ordering temperature is 5.2, which is much higher compared to the magnetic ordering temperature for the zigzag. And this suppression relative to the linear chain is because of the JF. Now, if you're not convinced, by the way, these are the crystals that we have grown in our lab to probe these materials by the float zone method. So this becomes more apparent when you dope just 1% of cobalt in these chains. So by doping 1% cobalt, what you're doing is you're just amplifying this effect. Why this effect is getting amplified is something that we will discuss over the next few slides. But what you see here is that in the case of the linear chain, where there's no frustration, the zero field cool and field cool data completely overlaps. All right. On the other hand, in the case of the zigzag chain, where there's frustration, the zero field cool and field cool separates out. So there's a thermomagnetic irreversibility, which is a sign of presence of frustration. Now, in order to show this further, we did more detailed experiments, and these are actually reported here in this PRL paper. You get the characteristic frequency dependence, and from the mu-SR, we don't see oscillations, or you see very weak oscillations, which indicate that you have these puddles of ordered regions, which can be probed by the which were probed by the neutron experiments. And you see that the puddles, their size is about 12 unit cells perpendicular to the chain and about 40 unit cells in the direction of the chain. This work was done in collaboration with Christian Rüegg and Marcos Koulatos. And the mu-SR experiments were done with, sorry, I'm not recalling the name of my collaborator. I'll come back to it because it's there in the last slide also. It's not a very old work, just 17, but somehow it's not just occurring. Okay, so if you're interested, I can go on and discuss why cobalt doping has amplified the freezing temperature in the case of zigzag chains and nail temperature in the case of linear chains. So you permit me to go further? Just show 2 or 3 slides. You have 5 minutes including discussion. So okay, so I'll just show you this slide because this has very interesting data. So here we show the specific heat as a function of temperature for various cobalt dopings. And you see that as you increase the cobalt concentration, the temperature, so this is for the linear chain, first of all, because now we want to understand what cobalt is doing. Therefore, we will not touch the messy system, which is the zigzag system, where there are 3 interactions to deal with. So we go back to the linear chain system where there are only 2 interactions, and we see that the pristine sample orders at some temperature near 5 Kelvin, and then this is how the ordering temperature evolves. Now, if you plot the ordering temperature as a function of cobalt doping, you would see that even for a very small cobalt concentration, there's a sudden jump in the ordering temperature. Now, this you cannot explain by augmentation of J prime, because you cannot say that you have put 0.25% cobalt and J prime has increased, and because of that, the ordering temperature has increased. So our, in fact, the theory hypothesis rather is that this is happening because there's a change in the universality class. So to begin with, this is a Heisenberg chain system, and cobalt is an Ising impurity, though it's spin half, but it's a Ising spin 1/2. And that Isingness of the cobalt actually get transmitted to the entire chain because of the strong PD hybridization. So we have actually, tried to show this more rigorously by doing more experiments, but since I don't have time, so I'll skip these details and directly come to the phase diagram for 213 with cobalt doping. So this is how it looks like. You have maybe very quickly. So you suppress the order in the presence of a magnetic field, and at very high magnetic field, a new ordered phase appears. So the phase diagram looks like this when you apply a field along the chain direction. But when you apply a field along the perpendicular direction, the transition temperature doesn't change, which is, okay, so it's not shown over here. So this is what we believe is happening actually. We think that it's a, longitudinal antiferromagnetic ordering in the presence of cobalt in the absence of a magnetic field or in low magnetic fields. But once you start applying field along the chain direction, you get into this phase, which is the longitudinal spin density wave phase. All right. And once the field exceeds a certain threshold, you get into this transverse antiferromagnetic phase. And this is actually governed by these exponents of the Tomonaga-Luttinger liquid. This is the phase diagram. The field axis, the magnetic field, and here is the epsilon, which basically is the, determines how Ising or Heisenberg-like your system is. So when epsilon is 1, it's a Heisenberg Hamiltonian, and when epsilon is 0, is the Ising Hamiltonian. And if the system is somewhere in between, the theory predicts that in the presence of a magnetic field, you should see these transitions. You see the transition from a nail-ordered state to, to this spin density wave state, and then to this transverse antiferromagnetic state. In fact, this system, which has generated a lot of interest, which is based on cobalt, shows us a phase diagram. So there's a similarity between the two. But the nice thing is that here we get this just by doping 0.25% of cobalt in otherwise Heisenberg chain. So let me thank my collaborator. So here's the name, Giacomo Prondo. So I'm really sorry that I couldn't recall this name at the time when I should have. And the Raman experiments were done with Ajay Sood and Surjeet Saha, who is now a professor at IISER Bhopal. And I must acknowledge my students who actually did most of this crystal growth work, and my collaborators, in particular Luminisa. These two people are from Orse, which is where I got introduced to the frustrated systems, and I started learning to grow single crystals. So this is Ramanathan Surya Narayanan and Alex Ravkolevsky. And these are my other collaborators whose data I showed in this presentation. Thank you for your attention.
Thank you, Surjeet. Very interesting talk. None of us would be here without materials. So, questions, comments?
Cobalt replacement in the zigzag.
Correct.
Now, are you sure about the spin state of cobalt? Because cobalt is susceptible to low spin state. So, because then there is a possibility of chirality coming in, because cobalt sits and isolates 3 spins.
Correct.
And they can be chiral ground state. And
yes,
new physics there.
That's right. That's right. So we don't have any, experimental evidence that cobalt is indeed spin 1/2. But based on, what we have seen in the case of other systems where the cobalt sit in a square planar coordination, similar coordination, based on that, we sort of, hypothesize that cobalt has a spin 1/2 on it, effective spin 1/2. In fact, it would be 3/2, but because of the residual orbital moment, that will couple with the spin and you get an effective spin 1/2, which is sort of, in low dimensional system, this is more of a rule than exception that the cobalt goes into a spin 1/2 state, and it shows strongly Ising behavior.
Any more questions? Yeah, Ramesh.
Yeah, Surjeet, nice talk. Yeah, so I have one question about the triangular lattice, right? That double transitions on nickel based.
Yeah.
Right?
Yeah.
Yeah, so I think this series of compounds, apparently we have EGX anisotropy, right? Which makes this kind of double transitions at low
Yeah.
right? And there is a very complex phase diagram.
Yes, that's true. That's true.
But did you measure magnetization and see any plateau at 1/3 or 1/8?
Yes. In fact, we did. I should have the data. In fact, we not only see 1/3 magnetization plateau, but we also see other features in the high field magnetization. I didn't show it here because it's not. I hope I have it here. So yeah, this is the slide which I alluded to during my talk. So this is the neutron data, which is done with Marcos at Garching. And this is the magnetization curve in the ramp up and ramp down field. And here you see the 1/3 magnetization plateau. But in addition to that, you see other features, which is not very unusual because, in this triangular lattice antiferromagnets, you can have a cascade of transitions, which I showed here also. As you can see here, you get a series of transitions until you go to the field fully polarized.
Okay, the last question.
I mean, in the case of the molybdates, you mentioned that one of the pyrochlore lattice is ferromagnetically aligned,
Yes.
and the other is like a spin ice, if I understood correctly.
Yes.
So does it mean that you have like a spin ice material is some effective magnetic field, and you may see this?
Absolutely.
And
That's what I meant. That in the ferromagnetic background, because of the FD exchange, the samarium movements at low temperatures, below a temperature of 15 Kelvin, undergo this 2 in, 2 out kind of ordering. And this phenomenology, in fact, has been seen in more vividly in neodymium system, in Nd2 where you can also do neutron diffraction, which is not possible in the case of samarium because it has a large neutron absorption cross section. So there, in fact, you see very clear signatures, and because it is metallic, so it has ramifications on the transport. So because of this chirality that comes in when the neodymium goes into 2 in, 2 out state, you get this very large anomalous Hall effect.
Yeah, right, like in
this
the
material.
Takura. Okay, yeah.
This is a work from Takura's group.
Okay, let's thank both speakers and close the session.